So welcome everyone for Lecture 7, Deep Learning Applications in Clouds for our Cloud Computing and Big Data course. In the first part of the lecture, we really learned how to use basically one particular cloud instance, so to speak, this AWS with AMI instances and virtualization. Then we quickly learned that actually the Google Cloud does very similar things. They also offer, let's say, a virtualization image, but on top of that, what we learned in Lecture 4 with virtualization, the real benefit of this is that you have all these different packages already pre-packaged for you, readily available. And this is, of course, something once you try it out yourself and you switch a lot between TensorFlow and PyTorch because they have both their benefits, you will see that keeping track of all the different versions with all the different libraries is quite a big thing. And on top of it, what we forgot to always see is that the underlying infrastructure often change. So if you're in charge of providing these packages, you have maybe here and there a Kepler GPU, suddenly you're getting hold of a, let's say, Volta GPU, and now you buy basically an A100 GPU cutting edge. All of these have different versions of the libraries too. So everything what you did before also have to be migrated to new versions and libraries. And the beauty in the cloud is this is in a way abstracted away. Only in a way, because by choosing a specific instance type, you have to pay. Right, so an old Kepler GPU might be just $10 per hour, while a cutting-edge A100, which is by orders of magnitudes faster with tensor cores, we will learn this in Lecture 8, and so on, with having a very specific tuning for deep learning, for instance, this is then, of course, $24 per hour. And you learn in Rocco's lecture that we use, for instance, in research to 128 GPUs at the same time for many hours, right? And he will give you a cost breakdown, what it would cost for researchers, for instance, to go to the cloud, which would be impossible. But of course, a company doesn't have the benefits we have in science of having this for free. So hence a startup, or basically everyone that is using these services, should really very, very accurately look on the costs that you have there. We just discussed in the break, not only have you the cost of the GPUs, you have the cost of the software like SAAS, SageMaker, but you also want to have some data stored. So you have elastic block storage, also something we do in one of the coming up lectures. So you combine, of course, all the different services, and by this, suddenly your $24 per hour grow up to $50 or $60 per hour. Of course, the training of deep learning is also not always what you do as a company. Usually you do this, train it. Once it trained, it remains maybe stable for 3 months, and then you do something we call inference, testing. You basically can roll out the system and just use it. The inference itself is not so costly as training. So with this, you are in a way safe once your model is trained, but experience shows that basically companies that did once modeling, they will engage again, usually in it to make it better, to keep it, let's say, on the cutting edge of technologies. So this is the first part, and there are many different topics which I found interesting, which I cannot convey here in the course. I think transfer learning is one of them, which is by far an interesting approach. Anyone has used that or heard from that before? Where you actually pre-train models on something like dogs, cows. So these kind of simple, trivial problems. Once you pre-train such a neural networks with all the weights, you put it to a real problem, like we face in research, maybe pixel-wise classification, not scene-wise classification. So it's a valid idea, and you have seen the Google video, they provide you already natural language processing pre-trained models. Alone to do this, you would spend lots of money just going so far. So there it could definitively make sense to use this pre-trained models and adopt it, maybe as we discussed in the break again, a Chinese Icelandic translator. You not start from scratch, you go to the cloud, it's all pre-trained models, and then you tune the last bit, maybe basically from Chinese English models to go to Chinese Icelandic models. But this is, of course, something which should be taught in a machine learning course, or at least at the deep learning course, I think, from Magnus, that's the minimum. But we cannot put here all in this. But of course, the case is made that for these pre-trained models, cloud computing resources, of course, are very beautiful, and also the access to these models is very nice. Now let's look back a little bit what we did also the last time, because I promised you also here and there some refinements, just that you really understand a little bit what deep learning is doing. And I always make the point to the different computing entities in this course. So cloud computing, where's the problems with GPUs, with capacity, and so forth. Also in the Google Collaborative, what you use also in the assignment, there's a specific setting where you can actually switch between different resources, right? That's something which we didn't try it in the first part, basically with Spark, but you have hardware accelerators. And as you learned from one of the earlier lectures, is accelerators like GPUs from NVIDIA, just one example, make a big difference. Google has their own ones called tensor processing units. And we will look into this tensor processing basically in more detail when we have infrastructure as a service again. They are a very interesting way to really compute deep learning networks very fast. Hence, one part of your assignment will be also to switch between those from a normal CPU, right, that we know, a many core infrastructure like a GPU, and then tensor processing units like a TPU. And you can see in 5 years, we have there also a kind of graph PU or so, a graph processing unit. They're also very good for artificial intelligence, which we just have now in research. Once a TPU, I remember, was also available to us in research, and now it's basically there for everyone. But not forgetting that, of course, GPUs from NVIDIA are not standing still. By now, they have adopted the idea of this tensor processing and have also NVIDIA GPUs, which are exactly tuned for tensor processing, just for AI, for deep learning. Just to talk to you that, of course, not all is software, right? What we basically had here, the cloud gives us also unique properties really to access different hardware elements. What we have seen in Spark, we basically have all levels of memory, right? Which extremely cheap, which is making basically Spark useless because Spark was really benefiting from memory, up to a very graduate process of going to very extreme expensive, basically deployments where you have had a lot of memory, but of course where Spark then would be, fast as hell. You go and pay the price for this. And this is of course also a benefit for clouds really, because you as a startup facing that problem, you never know, should I go for cutting edge GPUs and really pay the price, or should I go to moderate GPUs, maybe older ones I get on the market from Kepler or Volta, which are outdated, but still do the job for a startup. Maybe it's not worse to go to A100s, what the cutting edge right now is. So all these different architectures matter and will be now consecutively following in lecture 8, lecture 9, lecture 10, and so on. This was just to get you early up to speed for the assignments. We here and there have some holes we have to fill, but experience shows we want to engage early in the assignments. Still, we were a little bit fast with all the ideas of neural networks. Admittedly, it was just one lecture. In normal machine learning lectures, you have much more time for this usually to actually explore that. If you want to understand this a bit more, I would encourage you to take a view on this particular tool. It's actually quite nice playground provided where you can play around, and we don't do this much here in the course. I think you basically can get the story where you can play a little bit around and understand the concepts much better of combining different layers and the power that we had essentially with these different ideas of linear separability. There are different data science problems that you can have here, where of course you can imagine this is a problem. And here we immediately knew when we have here discretize the output, the decision boundary, we knew that basically with this perceptron idea with one neuron, we cannot do much, right? When we do this, how we should find a line here, right? To separate something like this. We need a nonlinear approach to separate essentially these two classes. And one neuron remains essentially very limited to do this in a linear space. But we learned by combination of that in the last lecture, right? By doing much more neurons in the hidden layer, you more get to very interesting ideas of having kind of interesting shapes of functions that you can't see, because the powerful should be also, of course, on the other side of the output here, enabling more power in this. And by playing around with this, with different options, you can basically then create very nice decision boundaries and options where you then see much more basically how the training works. And over epochs, when you train, then essentially how the test loss gets basically down more in this particular one, and will perhaps create something which is at least better than the line we have seen before. Right? Thinking about now that, of course, we have still a very limited 8 neural network, right? We used 128 neurons in the hidden layer ones, for instance. So when you play around with this, adding more and more neurons and then starting learning, you can adjust the learning rate. If you remember, this was important in the stochastic gradient descent of how quickly we go to find the local minimum. It's a quite nice tool to do lots of different interesting things. It would fill a whole lecture because you can imagine you have different activation functions, rectified linear unit I was talking about. You can train. You have regularization entities that you also have in the assignment, the lasso regression and the lasso L1 and so on. So this is maybe a nice tool for you to understand it better if you're interested. So let's go further. And while these captures the essence, of course, in a way, to understand the more advanced CNN concepts, it's really now for you important to really understand what always was happening with this kind of multiplications again and again that we have seen in the neurons itself, like we had in the last lecture. So in a way to understand CNNs and convolutional neural networks is really beneficial to understand at least the simple ANN concepts before that, right? Because in a way, the CNN concepts are a bit more harder. And this is something what we discussed a little bit also in the break last time. I think we discussed what are the architectures, right? In our deep learning and so on. And you see here, one of the most famous ones in deep learning, admittedly out of date, it's 2012, but it was the first time really that a deep learning network kind of beat computer vision people. Computer vision people usually do a lot of work to do things right manually to get good accuracy in an image recognition problem. And that's it. We learn that things as machine learners, and actually over many years have tried to beat them, their specialized versions. And this was the first time where really machine learning itself could beat these specialized approaches. However, you see also the computing was not ready for such a thing yet. There were GPUs around, but you see here an artificial cut between the heart, so to speak, of this AlexNet, which was then broken into 2 GPUs because GPUs didn't have capacity at the time, right? 2012, that is just 10 years ago, and now we will laugh about this network. Hence, of course, there are lots of improvement, but in order to understand deep learning, we go there a little bit into this AlexNet initial infrastructure, or if you want an architecture topology, which really helps you in image recognition problems. You always could think about that here, the image would be coming in. So you have an input part of the image, which is maybe 222. So this is a very specific architecture, but of course you can modify it. And that's what usually people did all the time. They start with a very known architecture, and then you would start adding convolutional layers or adding, different neurons in all of these different layers. You see always these interesting numbers, which reminds how many neurons are in these layers. And nobody told you that this is good. Also, the AlexNet people, of course, they tried the experiment to put so many of these neurons in. And at some point in time, it just got better accuracy as all other competitors in the so-called ImageNet challenge. And you have different kernel sizes. That's what we want to look at today as well, because I think not all of you know the difference between kernels, filters, and what it means to have strides and padding. So we will go that again and again, and also reflect again why it's so heavy on computing and why you need actually cloud computing resources for that. So essentially you have here this input. You have 3 that's almost not visible, but you can imagine an image with RGB inputs. That's also what we had the last time. So this is the input layer, so to speak. And here are these so-called convolutional 3D structures. As I said today, people would not really cut that into this, right? This was an approach at that time. And you always have the same building procedure a little bit. You have this convolutional layer. There's a nonlinear activation function, as we know from last time, with a neuron that is sitting here inside these, and then a pooling to make a subsampling of the data. Right, so that's why it's getting, let's say, smaller and smaller, hopefully, because all of these calculations that you see, of course, take a lot of time. We also observe that there is not really so much a dense network anymore as we know from neural network we had the last time, where we said every neuron in this layer is connected to every other neuron in the other layer. That's what we call an artificial neural network. That's not what we do here anymore. We have advanced concepts called weight sharing and so forth. So, and I will come to weight sharing, why there are benefits in a moment. That is just the overview. And of course, now the interesting thing is the strides, how often you go over the data or basically how explicit you go over the data. That's what we also want to look at. You can make it quicker, but maybe you lose certain elements of the image, or sometimes it maybe even not fit. Then we do something called padding. to add to the different layers. And these are all concepts of convolutional neural networks that are maybe not obvious to you right now, but that we want to talk about it. Now, in a way, what you think and what you see is kind of this 2D with another dimension that is actually always making it so blocky. And this blocky character comes from the idea that any of these convolutional layers is not anymore, as you have seen, essentially this neurons from the 1D vector in the neural networks. Now it's 2D. And the 2D is augmented with different feature maps, right? So I can search now inside these images for different features in the data. These all are basically completely separate from each other, right? So we're talking here about a 3D structure, which is in one layer, right? So remember the one we had this normal neural networks, this was just one neuron and the long vector of it, maybe 128 vector of neurons. Here, the neurons are actually positioned in a very specific way, not only 2D with height and width. Here we can also steer the amount of features we want to search for in the data. So that is an important element. So in the sense, we remain, of course, kind of 2D, but want to carve out features essentially in this different domain. And what we do here then is again doing this principle of the convolution with striding over the data. And that is what makes it so computational heavy. So let's look into more detail. So when we do so, one of the key ideas why basically they really fly the CNN architectures are different, let's say, very much benefits that come from two kind of elements. The one is translation invariance. It's a bit loaded topic, but I think relatively easy to understand if you look at a little bit from the outside perspective. So for us as machine learners, that means essentially no matter how it is rotated, the image, right, we will still detect it. And I make a case later why. Also, when you have this translation, that means it doesn't matter if the elephant is on the left or on the right of the picture. So we still can detect it. And this is a key difference to normal neural networks, right? They can't do this. They lose the spatial connectivity. They can do it by doing more and more hidden layers and neurons and have another strategy for this. But here, the idea is that we can kind of capture this as a more global perspective as a CNN. So this is one part of it, right? So this kind of translation invariance. And that actually beats lots of different networks with this. The other element, which is quite interesting for us, which enables this, is essentially this weight sharing, which says, if you remember the last time we had a neuron is connected with any other layer, basically, and then we had lots of different connections, and all of these were weights to train, and all were different weights. Now, what these are now doing is that each of these different colors, so in a sense, every feature map has basically just connections to the others in a certain particular way of the kernel size only. And I will come to this in a moment, but essentially this means inside the layer of the convolution, these are not connected, right? You just have a big block and they are standing separately. And all of these have the same weight they share. Fundamental difference to neural networks before, right? They had every neuron has its own weight with every other neuron in the next layer. And here you basically just share the weights with everyone in your feature map. Why? Because then I'm able with detecting the weights in this feature of actually don't worry about if it's in the upper part of the picture or in the lower part, the weight. And we come to the moment that we do this, of course, not per one pixel. We do this per kernel, could be 3 by 3 or 5 by 5 to detect the feature, even if it is rotated or translated. I have several examples later that makes it more clear. But it's really important that you understand this particular part here, right? There's all these neurons with the same color here. These are identical weights. Otherwise, when we do deep learning, we would so heavily swimming in parameters that would be computationally infeasible, right? And also it wouldn't work, it would overfit immediately because we would have still, let's say here, this is 5 feature maps or 4, then these all connected with different weights to the next layer would be orders of magnitudes much more weights. And the weight sharing is now the benefit why this basically works. So in one sense, this enables us something which we lost in this neural networks. If you remember, I told you at one point in time, instead of looking at everything at the same time, we have to vectorize it, right? So basically you have a long vector in this dense standard case. And basically one of these neurons is now talking to every other neuron in the other layer. So these are all the same weights, and you do the math. We always have, of course, this kind of summed up linearly using weights idea, right, of every step, and then doing essentially the error and going downhill with the optimization. Now, the idea with this locality, which is now the idea of this, let's say, receptive field, as they call it, is to connect not anymore all of those, basically, to all the others, but keep it in a so-called receptive field and move over the data set in a certain stride. And of course, then you see also from the colors, essentially do a so-called weight sharing. So instead of saying this is one feature map and it will be going to the stride of the next level, you just keep the same weights. By this, your order of magnitudes reduce the number of weights alone with this locality. But of course, by weight sharing, you again kind of basically get rid of lots of different weights you have to carry around. Still, of course, for all the weight metrics you have and share with all the neurons, you have to do the math, right? You always have to multiply for each step, going from one to the next layer. But in this case regard, it's actually this weight sharing going on. And by weight sharing, you can have then this translation that you detect this figure no matter where it is, if it's rotated and so on, right? Of course, this comes more clear when you go deeper, right? So just having one layer wouldn't do the job, you can imagine. So basically, as you have seen with the sevens, I demonstrated with this website last time, right? When we had the 7 with the smaller features, breaking down the 7 in smaller, let's say, parts of it, you have to do it, of course, deeper. Just doing once a feature map and then from that another feature map is not really helping. You have to do it deep, hence the name deep learning network. So what you do, and this is what you have in lecture 6 already as the example, you have the set of weights that we call then a filter and move over this data. Here's an example where we do this very explicitly with stride 1. But if you do stride 1, you can imagine you do very little progress in a way. So in a way, your input image is almost as big as your feature map. Hence, you could also think when you have a 5 by 5, let's say a window here, that you do a stride 5, and then at least you detect still lots of things in the image, but are much more quicker, right? Of course, here's the idea that maybe some features are overlapping. So it would be better to do a stride 1, but you see you don't really get, let's say, less computation very much, although they also share the weight. But now you can think about it like a rudder. You know, by doing this, we actually found something like a rudder piece that will search for a certain feature, which is always in this kind of size. Even this is the edge, a corner of a certain size from this ape we have seen, and will detect that. And basically, then over time, you come to smaller and smaller features of this. And the stride is now, of course, a major idea how you can make it quickly smaller, plus the idea of this pooling we discussed last time. But just that you understand, firstly, this convolutional filter that is applied. Here you see one example of the filter by 3 by 3 going over and just strengthen the signal or weakening the signal. And of course, this filter will be learned over time because we have always this guiding output and do this chain rule of backpropagation and will also update these weights. It's not that we have just one filter defined with these numbers and go over it. Of course, this will be learned over time to make it right so that the convoluted features or convolved features really are getting to certain shapes over time. That's why we still need lots of epochs to train, right? Otherwise, when this perfectly would work with the filter, then we just would go once through the data set. But here, the epochs will make it right that by knocking the error down, we will actually learn these filters, which are nothing else than a set of weights on a receptive fields on a very interesting, let's say, small idea. But by doing so, you preserve the spatial location, right? If you remember, we don't have this long array anymore from this neural network. Really, with this, we are detecting the big picture, if you want. That's what they say sometimes when you do an explanation on this. So from another perspective seen, we have, again, our little neuron here. And basically, the next one to connect to will be then something like we see here. We have to have a filter that then basically for each of those, we go over it and look if it fits. The question if it fits depends now on your kernel size and your stride, how much you basically go through it. As the RGB example here, you could have, let's say, highly overlapping, right, with a 2x2 kernel. And this would be now 3 neurons in the next layer, right, that it connects to, this 3 which are overlapping. So it means if there's a feature in this, all 3 will fire, right? When you have a stride of 2, it just will basically be kind of collaborative from the space it covers. And if there's a feature just in one of those, of course, it will just fire this. So in the end, you define the architecture also with this, and the stride will determine a little bit also your kernel size. And with this going through patches, essentially through a whole big image, right, which is here just 8 by 6 or so, you of course firstly have to see if it fits. If it not fits, that's not a problem. We call it padding. We add just artificial zeros here so that the kernel can still proceed. And you can imagine when you do multiplication, it's nothing else than this, just multiply something with 0 padding means 0 signal. Of course, we also don't expect then that here would be a feature on the data. It will be in the image. So the padding is basically our helper when it's getting too big. And yeah, this is the kind of idea how you basically craft this in the beginning. And again, think about that this is only working so nicely because it's sparsely connected. Sparsely in the sense that not really, this neuron is now automatically connected to every other, but in the idea of this kernel size, and then having this convolved feature created. This is called sparsely connected, opposed to fully connected. So how we can have a practical example, right? So I think it's always good to see how we human judge this. And in the beginning of the course, we did this with a flower. We said, what was, in lecture 2, the idea of a flower? We as humans were looking on petal length and petal width. We didn't check now every pixel and looked if it's equal, right? Even if remote sensing, I gave you some examples. If there's 1 pixel in water in our research, then of course there's a likelihood that the neighborhood pixel or one of them is also water. In a normal neural network, you kind of lose this information, but with the patch view, right, of this neural network, you directly actually get this feature in. We don't encode it anymore as we did explicitly in neural networks. There we put petal width and petal length in, if you remember. Here, the neural network does it itself. It realizes in these patches, there's again something like this. There's again a petal width which is getting out of my patch, and there's some that actually fit in my patch. So these must be different tracks in the deep learning network. And with this, over iterative solutions, you come then to the idea that these are different classifications. A very simple example, so think how humans would work. A cow, I had another example. A cow, we don't identify by counting all the interesting, different colors on the cow. We just know parts of it. This is probably a cow because it has this interesting pattern. Pattern is a good idea to think about. That's what we can do in machine learning very well. We look just what is the input problem, which means we have essentially an X, but we know from mathematics, this is not what we can use with mathematics by doing it pixel-wise, right? If you combine these pixel-wise, you have a very high error rate, but essentially still as a human, you would say to 70% it is an X, but you cannot compare pixel by pixel, then you have a very high error rate. So mathematics is at the end. We need machine learning to understand the bigger picture, these patterns. And by doing so, these patches are so incredibly relevant here. And by this, we humans also determine what is an X, essentially going through these different X's. Or we do the flowers with petal lengths, or we basically see in remote sensing our neighborhood. So this principle of locality is really a key thing in this, to really understand the convolutional kernels and why they extremely work so well. And there's also no difference if the X is this way or that way. So basically it will still fire. And with this filters is now exactly what you basically apply to it by strengthening the signal again and again. We go through the data set again and again all the time. And having here essentially the input data that we take, and then having the filter strengthening or weakening the input by multiplying it again and again. And by doing so through the whole deep convolutional neural network, you basically get the class information Is it an X or is it no X? But if it was an X, then do the error update, right? And so we go backwards. This is backpropagation, update the weights and go again. And by this, the filters on the weights with it, right, basically get learned over time. And making the patch right to detect exactly these features is part of the access. So in a bigger scale, when you think now not access, but cars, it works exactly the same way, but on a bigger, let's say, dimension, of course, right? Where you think about that now we actually are here thinking about the different kernel sizes, of course, but you have these different channels, the different feature maps you basically create. And with this are actually in a very good position to do the same thing again and again, iteratively. If you see convolution, ReLU pooling, convolution, ReLU pooling, convolution, ReLU pooling, always the same thing. We didn't talk too much about the pooling yet. I think that's what we had already in lecture 6. It's very clear that we can always downsample. Sometimes we have to do it. Sometimes often is use a max pooling because it means the strongest signal in this feature first, right? So from 4 neurons, you go down to 1 neuron as an example. And it helps, of course, again, for doing the computing. And here's again the idea of the indicators why we never get 100%. No matter what you try in deep learning, because humans also can't do it. Yeah, and summarizing a little bit and comparing it with neural network, we said every neuron was connected to every other one, right? And this was extremely costly to compute, but also very prone to overfit if you keep doing this with deep learning. So what essentially machine learners have done, creating features and giving them into the neural network to make it faster and to make it better. And all of this is now in deep learning itself. So we have parts of the network doing the feature extraction, the feature learning, do it for us, like the PETAL and CEPAL understanding. And then basically we have the label, which is of course important for us to learn back and forth with a kind of backpropagation of error, and then maybe do the decision later. And every time I actually do this tensors through the network, hence the name TensorFlow. It's nothing else than doing this multiplication all the time. And this works very well, as you see, for cars, for trucks. Here's just important to see that it's never 100% because some features are, of course, shared with different classes. So here you see that a car is actually also part of a truck. Why? Of course, a truck has wheels. So this feature wheel is always hitting. While, of course, the wheel is maybe bigger, the network learns in these convolutions to abstract in different feature parts of the wheel. So that could be some trucks which have the same size and still would fire. Same with the airplane, it has smaller wheels, still the same feature, right? Of course, the other features are missing, maybe like front lights in this height and having a proper Tesla display here, whatever. So it's very eminent that there's a high probability for a car. But this shows you also that the last bit is always a probability distribution in the softmax layer based on all the features to combine them. Summarizing, actually, of course, CNNs are just the beginning of the story. So here we have this feature learning part. This is convolution operations and pooling and playing with the rectified linear units. That's also what you do in the assignment. You will play a lot with the architecture. Once you have done all this feature learning, you have this typical old traditional flattening, doing a proper neural network on top to do then the decision. But this kinds of feature learning is not anymore done by humans. It's now done by the machine. And now you can imagine doing a car recognition problem is one of the most simplest problems we have in machine learning. It's a scene-wide detection that we call. And what we do in proper research and engineering is really pixel-wise classification, which also Rocco alluded to. So we're not interested in the whole scene of the picture. We have, let's say, satellite images, which look 200 dimensions into the Earth with spectral channels of light and reflections. And by this, we want to understand each different pixel. Is that water or what type of material it is? Rocco will make this much more explicit in his talk. And you can see that the real problems we have in machine learning are much more complex. So we need much more deeper networks and much more complex networks. He will talk with you about the so-called residual network and how we then also use, let's say, 96 GPUs in parallel in the cloud to make that happen, because this is impossible to do on a laptop, right? And this is a cutting edge architecture, ResNet 50, which is also getting out of date because now we have ResNet 100 and also much more deeper levels. They have the skip connections called these residual parts, which here and there are helpful to just keep some features which are not so that evident. And of combining then different GPUs together is also not that simple. That's why Rocco will talk about distributed deep learning, which is his research. Basically, he does as part of his PhD. But this will come on Tuesday, so I don't want to spend much time on it. Of course, high performance computing, the other course I teach, are partly underneath doing the technology for this learning. You see Spark is also eminent and MapReduce is often used, but still MPI is most used these days to really do multi-GPU training. And then at the cutting edge, at the end, so to speak, you have neural architecture search, where we will go to also in later lectures a little bit, where you have basically the computing done, or this learning of the architecture itself. So you have several objectives, how to create these different architectures and build layers on its own, right? It alludes a little bit to AutoML, but neural architecture search is really much more elaborate. It uses reinforcement learning partly. It can use, let's say, also generative algorithms to really create different architectures also for different problems. And of course, this is something where now it's cutting edge research. It's just good for you to understand that, of course, people have thought now, understanding deep learning, now the next step is how we can do basically and automate the process. To give you a glimpse also what is much computing intensive are recurrent neural networks. Now we have image recognition, which is rather simple. When you have sequence models like language, or we did some studies with Landsvirkjun in the Icelandic power company here for the detection of energy in lines and so on. You have so-called recurrent neural networks that not only have a neuron, it's also, again, basically connected to itself, recurrent, in order to capture the time dimension, right? Because every neuron will be existing in a certain time in a sequence. They are traditional RNN models. These days in deep learning, we have this long, short-term memories, and this would fill 3-4 university lectures just to give you an idea that we just scratched the surface of deep learning with image recognition. In sequence learning, we can do much more. In all the language translations these days, we have LSTMs working very effectively in ad hoc manner. But you also see the price for it there. Instead of normal recurrent neural network structures with a gate, we call that and so on for learning, you see here 4 gates or so inside the cell and then unrolled over time. So the computing complexity is massive here and actually also requiring then basically clouds. And this could be for many different signals, speech, of course, medical signals, sentence and natural language processing. And all of this is also supported in the different models we have. We already do lots of research with autoencoder technologies, where you try to get a latent space of features out. This is something where I guess Rocco will also talk a little bit about it, where you can then reconstruct images out of very little, let's say, compressed features, which make them the essence of the data. This is also a large set, basically, of deep learning models called convolutional autoencoders or autoencoders in general. And last but not least, then the kind of idea of using it in the cloud. This is one of our research papers, what we did by using just beautifully Spark on it, because also here, the idea is, of course, you can do deep learning in these Spark clouds if you want for very specific problems by deploying the deep learning networks on all these different worker nodes. This just should give you a little bit of broader perspective why, of course, there are deep learning courses. I think we also go in research that far that we say today you need professors for deep learning only because it's so rich that even machine learners don't know all the details of all the deep learning, but it's possible. In fact, because you also combine them, like we see here and there, CNN combined with LSTM over time, which makes it for image or basically for video recognition, the best to do. And here's a self-driving car that we all know. Actually, the ministry is just crafting, I think, something for having a legislation for this and so on here in Icelandic roads. Here you have, of course, not an image.
Maximum speed 50.
I mean, this video is much more to say that all of this, what we just seen, is actually in real life now on the streets.
Maximum speed 70.
We're actually detecting all of these things. And in the future, we will not even think about this anymore. It will be just normal. Of course, this depends on speed. There's also people that are
Maximum speed 100.
And so on from this. Right, just that you know how the inference now works on the deep learning. It's very, very effective once it's good trained. And yeah, as I said, also the inference, once this deep learning is trained, it is actually very fast. That's the beauty in deep learning. Once the training is done, you have a very good network, the inference is just like a click. You see, even at night, this is here and there working, of course.
Maximum speed 30.
There was once in Silicon Valley with a friend who was doing this, and we had to brake sharply in a Mercedes, so because it was failing.
Maximum speed 50.
And I think we're getting there in machine learning.
Maximum speed 60.
All right, so this is not a 5-minute video. I think you get the story, just maybe 1 or 2 more.
Maximum speed 70.
Maybe this is still okay. Good. So I hope this was getting a bit more clear with the convolutional operations at least, and why they are so effective in this particular lecture. Of course, when you do the assignment yourself, my hope is that this will much more deepening the knowledge of changing epochs, changing regularizers, changing the architecture, that this becomes more in your blood in the cloud. And that's all for lecture 7. So thank you very much.